We have a request to do Fall 19, Test 3, Part 2, the spiderweb version of Part 2. That's the alkene reaction portion of Part 2. Here it is in its fullness. We got it over here. And we're starting down in the middle. You'll be starting in the middle of yours too. We have a reminder of our isotopes here. Remember, deuterium is an isotope of hydrogen. The chemistry of deuterium is identical to the chemistry of hydrogen. But when a deuterium is present in the molecule, you need to draw it because it is not identical to hydrogen. It has a mass of 2. Same for tritium. Symbol is T. All right, so I'm going to draw my ring once nicely down here. I'm going to draw the rings without the pi bond because we're reacting the pi bond. And I think that's nice enough. And we'll group it, make it a little smaller so it fits in our boxes, and start putting it everywhere. All right. The only box I'm not going to put it in is the box that has ozonolysis. You know why? Anybody? No. Is there an ozonolysis here? Yeah, there is. Bottom left. Ozonolysis will actually open up the rings. But you know, I can still copy paste it. I would have to erase the bond between the 2 carbons in the alkene. But instead, I'll draw it when I need it. 2 more, 3 more. This is very therapeutic here. All right, want to go straight up first? Why not? We're using D2 and PT. Sorry, DD. So you'll get half credit for drawing just that. Half credit if you draw D and D. But we want full credit. Sin addition means either wedge wedge or dash dash. You pick. So I'll go wedge wedge. Wedge 1, wedge 2. Good. Right beside it is another sin addition. And in fact, this is just the osmium O4 reaction, and then it's followed by the reaction that breaks whatever's in the box down to a diol. And you know, you want to see that diol, and there's sin again, so the diol, it's not worth any points because I've given you that product. It's, well, don't do that. Please don't do that. Here we go. All right. We got OH as this diol right here. And before you get that diol, there's an intermediate called, now some of you may not have read this, it's called an osmate ester. It comes from osmic acid. And it has the 2 O's. No. You only get the OH after you add this chemical, whatever that is. And, oh, you convinced me to draw an OH. Look at that. I didn't want to. I wasn't going to draw it, and she convinced me the power of suggestion was strong. No, we don't. Some of us don't know this intermediate looks like this. It has OS here. Make sure that's a small s, everybody. If it's a big S, that's oxygen and sulfur and a unicorn. There it is. Osmate ester is what you get if you don't add this chemical to break down the osmate ester. Tert butyl hydrogen peroxide. OWL uses a different chemical almost always. In fact, I think always. OWL uses NaHSO3. Sodium hydrogen sulfite. It does the same job in terms of the overall chemistry of the organic molecule, it does the same job. There you go. So that's a new twist there, osmate ester. Okay, nice. Now what chemicals, in fact, before I do this one with the mercury, clearly there's mercury in this one. There's another reaction with mercury over here, and it's got the two parts. It's got the two parts. So the first part's called oxymercuration. Same as this one. It's got a new oxygen on the more substituted carbon and a mercury on the less substituted carbon. So that part has the same chemical as this part, HgOAc twice, but stop there. HgOAc twice. I know you want to add water because you've learned the reaction with water. But remember, I'm just trying to erase this thing. It won't let me. There it will. It was too far away. Water puts an alcohol on the more substituted carbon. This is not an alcohol on the more substituted carbon. Instead of OH, it's O-methyl. Water, you use HOH to put OH on. What are you going to put OCH3 on? Don't tell me HOH. Tell me HOCH3. And you get full credit. It's called oxymercuration for a reason. It doesn't have to be water. It can be any alcohol or water, or even a carboxylic acid works here. But I won't do that to you. I will have either an alcohol, which makes an ether, or I will have water, which makes an alcohol. Sorry, I'm doing them out of order, but they surely belong together. And I'm not going to put mercury on the end of this bond because step 2 is called demercuration. Please don't have mercury there. If you've done demercuration, put whatever's attached to the boron in sodium borohydride or sodium borodeuteride. You don't need to know that name. That's the same as sodium borohydride, but it's got a D. So put the D there for me. Okay. And in this one, I want to get rid of the, how do you know the mercury's gone in this one? In this one, do you see mercury in the name? No. Do you have to know what methoxy means? I bet you can guess now. The good students should be able to guess. What part of that name is the methoxy? I know you've never seen it in nomenclature, but that shouldn't scare you. Look at the whole molecule that's drawn right here. Tell me which part's the methoxy. OCH3, methoxy. So that's a chapter 11 preview for you. That's an ether, and that's a way to name ethers. So it's got the methyl on the same carbon as the methoxy. Cyclononane means this has to be an H. How do you get rid of the mercury and put an H there? How did you get rid of the mercury and put a D there? That's what this did. So what am I going to put in this box? This replaced the mercury with a D. What goes in this box to replace the mercury with an H? NaBH4. We have to know that chemical. And now it's not a question mark, it's an answer. All right, now, this one, we do have to know this, 2-methylcyclononanol. So 2-methylcyclononanol. 2-methylcyclononanol. So hey, you know about nomenclature of alcohols. If I put the OH there, what's that carbon number right here? 1, 2. I think I just drew the product. What's this question all about? Well, if we did the question before, I think I would have had to do even less thinking than this. BH3, 3 points. Whoa. 3. You got to know 3 things. 1, you got to know it's a syn addition. 2, I did 1. 2, it's Markovnikov with the less electronegative B on the more substituted carbon. The more electronegative H on the more substituted carbon. So 2 out of 3 points. Syn addition. I kind of like wedge dash on this. A wedge on this, sorry. And the more electronegative H on the more substituted carbon, the less electronegative B on the less substituted carbon. Now your third point is for the students who know that the stoichiometry in this reaction is 3 moles of alkene for every 1 mole of BH3. It's because each H reacts, and it reacts exactly the same way, syn addition. So how are you going to get your third point? Do you want to draw this ring 2 more times on my boron? Please don't. This is when you do an R group. You circle the R group. And I tell you, every semester I'll get the students to copy everything except the circle. They say, oh, I'm going to say BR2 there. You're going to get 2 out of 3 points because you didn't show me you knew what R was. R is anything until you tell me what it is. So that circle is part of the third point, and the 2 R's are the other part of the third point. It only happens in this reaction. So no, don't do it for any of these other reactions. Well, how are you going to show me it's those particular carbons in your R group that put groups on? I think he's asking, can I do it up here for this and just write R, OH, OH? I'm going to give you a zip. What 2 carbons have the OHs? Not clear from your circle. Don't put that on the test. Bite the bullet, draw the rings for all of them. If there's an identical ring attached to the B, there you go. And then what's the chemical that gets rid of the boron and puts an OH in its place? It's not 1 chemical, it's 2. H2O2 and NaOH is a good choice. You could write OH negative here, I don't care. You can leave out spectators anytime you want. That's the oxidation step, isn't it? Gets rid of boron and puts an OH in its place. And hey, I didn't even need to draw this molecule in the end, did I? There's no boron in this name. So boron's gone. There's an alcohol in this name. OL is alcohol. So you got to know the step that gets rid of the boron and replaces it with OH. That's that 6-part mechanism with acid base in steps 1 and 6 and boron going from 0 to -1 to 0 to -1 to 0 and done. Yeah, the W. Moving along well here. Hey, we did this in the multiple choice, didn't we? This was a 2-pointer because there's both regioselectivity and stereoselectivity. More electronegative oxygen in water ends up on the more substituted carbon. Less electronegative halogen, Cl, ends up on the less substituted. They have to be anti because there's a triangle in the mechanism. They're on opposite sides of the ring because of the backside attack. And there we go. Moving along. Ozone. Oh my goodness. I really asked it this way. Wow. I won't be doing this on your test. I'm just straight up confessing. I'm going to be going straight from there to here, and I don't even want you to draw. I didn't teach any intermediates in ozonolysis, and you're not responsible for intermediates in ozonolysis. So I don't know what was going on in fall 19. I expected them to do the intermediate. If curious, see text. If curious, comma, see text, or the key. Fall 19 keys got the intermediate there if you're curious. So I'm not going to test you. But I do need to know the second chemical for ozonolysis that breaks this molecule down to this thing. And if you want to look carefully at it, it's this picture here where we have a carbonyl here, comes up to a ding, 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 ding. And that's 1, 2, 3, 4, 5, 6, 7, 9, 10. And that's it. Aldehyde on the end. 7 more carbons gets you to 8. 9th carbon is a carbonyl. 10th carbon is a CH3. That's the same. It's ozonolysis. And what's the second chemical? There's a clue. The second chemical better have sulfur in it, because I don't see sulfur in here, do you? That's a clue. And it's where the third O goes. That's another big clue. Give me everything except for the O. And you got that other chemical. That's the other chemical. That's the one that breaks apart that intermediate that I don't want to draw because I don't want to make you draw it. Usually I ask the question, like 99% of the time, I want you to give me the product. I'm probably going to do that for you. And it is the easiest thing to predict. You get your eraser out, you cut the double bond in half, and you put a carbonyl on each side. And that is what I just drew here. So I'll be asking for that kind of thing more often than this kind of thing. All right, now we did a reaction with Cl2 and water. Why am I pointing that out? Because it's the same reaction as bromine and an alcohol, except water, which is HOH, puts OH here. This thing, which is HO isopropyl, puts this thing on the same carbon. It's the same reaction. There's no difference, except the product is different. You get an ether instead of an alcohol. They are the same in terms of regioselectivity, Markovnikov, and stereoselectivity, anti. Whatever we can do with water, we can do the same reaction with alcohols. That pretty much holds all the time. Okay? I'll circle that, be consistent. The H goes away because it was part of an oxonium. HCl, that's our first reaction we ever learned. Major, minor, 1 point each. Markovnikov, Cl on the more substituted carbon. Anti-Markovnikov, Cl on the less substituted carbon. Minor. And that brings to a close that one, and I'll let you take a big view. What do they call it? The 10,000-foot view here. And there you go. Got everything. So you're going to have a spider web as your first question, and a little roadmap is the next one in part 2. Very similar to fall 19. And that's all we got for this one. See you on the next one.